Welcome to a lesson with Dr. Powell. Let's take a look at how we can compute the derivative of x to the fourth using limits. Okay, so we're going to think about this curve and think about a point here, an x value, x, so just at a particular point x, we want to find the slope of the curve. I'm going to do that by approximating the slope of the tangent line here, but we're going to find the slope of that by approximating by an average rate of change, a point nearby. I'm going to pick, so have an x value of a, an x value of a, and an x value of x. So the run is going to be a minus x between them. And we want to know what the rise is. So we can kind of write out what those points are. We have a point where we're plugging in a, and we have a point where we're plugging in x. We plug in a, we're going to get out a to the fourth. We plug in x, we're going to get out x to the fourth. Rise over run, so this minus this is the rise, the difference of y values over the difference of x values. We have a to the fourth minus x to the fourth all over a minus x. And we're going to be taking a limit of this as a approaches x. So the run is going to get smaller and smaller and smaller, and as a approaches x, the slope of this average rate of change line will become the slope of a tangent line, which is what we want here as a moves in closer to x. So the limit is a approaches x. So notice in this limit that a is the variable and x is constant. A is what's changing, x is staying the same, and that'll be important to us. Now, how do we compute this limit? Now, computing a limit often is kind of like a hole filling process. We have an algebraic expression, and what we want to do is we want to rewrite this algebraic expression in another form that has a different domain, different things that we can plug in. Right now, we can't plug in x for a. A is the variable. We can't plug x in for a because, well, we're dividing by 0. So we're going to rewrite this algebraically to an algebraic equivalent form where the domain is changed. So we can then plug it in and see what it's equal to. It's a very common technique of hole filling for computing limits. So to do so, we're going to do a division. We're just going to divide a minus x into this. Think of what these are. This is a polynomial. In a is the variable, x is a constant. This is a constant number. This is like variable to the fourth minus constant. That is a polynomial. And we're going to use a generalized synthetic division technique, or just a synthetic division technique in order to do this. We think about our powers of a. So we have a to the fourth, a cubed with a 0, a squared with a 0. These are the coefficients of the powers of a, writing out a synthetic division diagram. So 1 times a to the fourth, 0 times a cubed, 0 times a squared, 0 times a, and then the constant is negative x to the fourth, remembering x is a constant. Okay, and we're dividing by a minus x, variable minus constant. Ooh, you know what goes here? Well, if I have minus constant, it's the opposite sign. It's just the constant. It's just x right here. Wait a minute. Okay, if we're dividing by, it's synthetic division, if we're dividing by something like x minus 2, then don't we put, and there's different ways of drawing this. Sometimes you put a little thing here. I'm going to be just drawing this and putting it down there like that, the number. But don't you change the sign of this guy and put a 2 here. In the division process, that's essential because that changes the subtraction that usually happens into addition. Okay, so taking a look at what we have, we just go for it. We drop the 1 times that, so we get an x, drop that, multiply x times x, we get x squared. Notice this x is a constant every time here. Add down, you get x squared times x is x cubed. Adding down, we get x cubed times x is x to the fourth. This little box right here tells us the remainder, it's 0. These are the coefficients of what we have when we actually do the division. Here we're going to have different powers of our variable a. So this is like a right there. This is a squared, and this is a cubed. All right, So actually, that's what it's equal to. It's equal to that. Oh, wow. Okay. So it's equal to that. Remembering these are constants, and this is the quotient. We get that in this result of synthetic division. And then we just want to simply plug in x for a is the variable here. So we plug in x everywhere, and we end up getting, right here we get x cubed. Hey, we get x cubed here as well. Hey, we get x cubed here as well. And we get x cubed here again. This same type of thing happens often, even if we don't have like x to the fourth. If we have x to any positive whole number, we will see a similar type of pattern here. In here, we notice that we're going to end up getting 4 of these guys x cubed. It's 4 times x cubed. Notice that this has power 1 less than 4 here, and there's 4 of these guys, 4 of these terms. So we end up getting 4x cubed in the end. Similarly, if we had something like x to the fifth, how would that go? Well, you can run through this process, but you might see that noticing by analogy what's happening here, we had 5, we had 5 total terms here because we have a constant first power, second power, third power, fourth power. But because of the remainder that we were down to in our quotient, down to just 4 terms. 4 terms is the same as the power right there, and the 4 comes out as that coefficient. Notice that all these powers are, notice how these powers go up to x to the fourth at the end, but we're 1 shy of it here, and that carries through on all these terms, 1 shy. So it was 1 power down for x cubed. So in here, this 4 came here, and the power was brought down by 1. So if we're taking derivative x to the fifth, using a similar idea, we could see it's 5x to the fourth. Or if we had x to the 100, we could say that's 100 times x to the 99. Now, what if we had something like 2x to the 7th? How would we work that? Well, keep in mind that when you do our limit here, in our calculation, we'd have something like this: 2a to the 7th minus 2x to the 7th, all over a minus x, and we're taking a limit of this. Notice we could actually factor the 2 out, and then we're just making a similar computation and what we had before and taking a limit. So it's just 2 times what we would get. So really, this 2 multiplier, we can just keep on the outside, 2 times the derivative of x to the 7th, which would just be 7x to the 6th. So we end up getting 14x to the 6th. And that's a little description of using limits to think about the power rule, at least in a simple case, when this is a positive whole number. Thanks for watching.